Hello, welcome to the video. Today we are mainly discussing about two topics. The first topic is conservation of energy and the second topic is about cross section of elastic scattering. So, I think we can be start with the first topic, conservation of energy. We all are familiar with isolated system, right? So this conservation of energy is also related with isolated system. There is a law called conservation of energy. The law states that the total energy of an isolated system remains as constant, but it can be changes its forms. We can be sees this definition in another way, like energy can neither be created or nor be destroyed, but it can be changes from one form to another. From these two definitions, we can understand that the initial energy is equal to the final energy, and when we take its different, the numerical value will be equal to 0. So, that is the mathematical statement of conservation of energy. Then we can be moved to the subheading type of energies. We all are familiar with different kind of energy like kinetic energy, potential energy, thermal energy, and so on. So, what does you mean by kinetic energy? The energy of motion. When we take an example, like when a car is moving in a road, then the energy in the car during that motion is known as kinetic energy. And when that car is stationary, in that time also there will be an energy. So that energy is known as potential energy. And when we take uh, a bulb and when it was lightning, there is a energy in the form of heat, and that energy is known as thermal energy. Like that, there is also energy in electrical fields, and that energy is known as electrical energy. And when we take a refrigerator or like that, we can be take the case of refrigerator. The things we kept in that refrigerator was uh, will be fresh. The main purpose of refrigerator is keeping the items fresh during that period. So the magnetic substances in the refrigerator help for this purpose. So that kind of energy is known as magnetic energy. Then there will be also energy in chemical bonds. So the energy stored in chemical bonds are known as chemical energy, and the energy stored in atomic nuclear is known as nuclear energy. So next we can move to the general equation of conservation of energy. When we take the initial value sum of all the energies, it will be equal to the final value sum of all the energies. For example, let's consider kinetic energy, potential energy, and thermal energy. We are taking the initial value sum of these three energy, and it will be equal to the final value sum of these three energies. So that's it. So examples of conservation of energies. Actually, I have mentioned here four examples. The first is rolling of ball. When we consider a ball rolling in a floor, first there will be a kinetic energy, and then this kinetic energy is converted into potential energy, and again it will be converted into kinetic energy. And when we consider an object when it is falling from anywhere, it will just consider it was falling from a flat. So first there will be a potential energy, and this potential energy is converted into kinetic energy. And the third example is car engine. In car engine, uh, there are chemical bonds. The energy is stored in chemical bonds, that is chemical energy, and first this chemical energy converted into kinetic energy. And the last one is solar panel. In solar panel there are radiant, and radiant is converted into electrical energies. So what are the applications? The actually it was important in physics. So the first application is fundamental principle in physics, and second is helps to predict the energy transformation, and essential for designing efficient system, and it is applies to all scales from micro to macro. Due to the time limitation, I am not discussing about the derivation of conservation of energy. Actually, it was I just do this using the Newton's second law. Actually, it was so easy. I think you all can understand by the things I have written here. So the next thing is the unit is energy is joule and power is watt, and its dimension is ml square t raised to minus 2. So I just moving to my second topic, cross section of elastic scattering. So what does you mean by cross section of elastic scattering? Actually, when we consider two objects, and it is a measure of probability of scattering between two particles, and where the particles can retain their original identity and energy when the collision is over. So that is the definition of elastic cross section of elastic scattering. So what does you mean by elastic scattering? Actually, it was a process of interaction between two particles, and the final state is the same of the initial state, and there will be no energy loss when during this interaction. And the momentum and kinetic energy is conserved there, and the scattering angles are determined by the nature of the interaction. And the type of scattering, there are actually three types of scattering: potential scattering, example is Coulomb or nuclear, and resonance scattering, and the third one is diffraction scattering. So let's move to the applications of elastic scattering. Actually, it was applicable in mainly physics areas, in nuclear physics, particle physics, material science, medical application is also there, and also in industrial application and environmental monitoring. So what is its application in nuclear physics? In nuclear reaction and structure studies, we are using these elastic scattering, and also for accelerators design, particle designs, and nuclear medicine for cancer treatment like that. And it is also used in particle physics for particle identification and detection, and also for high energy colliders. So, in medical applications for radiation therapy, medical imaging, and cancer research. And like that, there are so many applications. Okay, next we can be moved to the subheading cross section. The cross section can be represented by the simple sigma. Actually, it is a measure of probability that a scattering event will be occur, and it will be give the livelihood of interaction between the incoming particle and the target particle. So its unit is actually in meter square or in barrel. So what is the differential cross section formula? We can be describe it like probability of scattering into a specific solid angle d phi is called the formula of for differential cross section. Formula for differential cross section. Uh, we can be described like it is the probability of scattering into a specific solid angle d phi. And when the scattered particle angle is theta, it can be defined, or it can be right like d sigma by d omega is equal to number of particles scattered per unit time into d omega divided by incident particle flux into d omega. So that's it. And what is the total cross section? The total cross section can be taken by integrating the differential cross section over all solid angles. So that is written in equation like sigma is equal to differentiation of d sigma by d omega into d omega. So that's it. As we all are familiar with Rutherford scattering experiment in plus 2 classes itself, and that is a classical example of elastic scattering. So, as we all know, the Rutherford do this experiment using alpha particle and the positively charged nucleus. The experiment he done is the alpha particles are scattered by the positively charged nucleus of an atom, and he gave a differential cross section equation uh, like the equation that I have written by there. So here the Z1 and Z2 are the atomic numbers, and E is the elementary charge, and epsilon 0 is the permittivity of the free space, and E is of course kinetic energy, and theta is the scattering angle. So why we are studying the cross section in elastic scattering? Actually, the elastic scattering experiment provide a crucial insight into the size, shape, interaction strength between the particles. And it is a key parameter in understanding the particle interaction in fields ranking from fundamental physics to material characterization. So, thank you for hearing me.